quantum conductance, derivation of Landor formula, Coulomb blockade, and an application of Coulomb blockade, single electron transistor. Let's take quantum transport in nanostructures. So, before going, what is a nanostructure? Nanostructures are materials that have at least one dimension between 1 to 100 nanometer. So, quantum transport happens in nanostructures when they are connected to external current by means of leads. Transport is also called mesoscopic transport. So, what does mesoscopic mean? The term mesoscopic refers to systems with a range of size between macroscopic and microscopic world, and that are to be explained by quantum mechanics. So another name of quantum transport is mesoscopic transport. Now, in order to observe quantum transport effects in semiconductor nanostructures, certain conditions are required. The first one, at a given temperature, quantum transport can be observed when electron effective mass is small. Electron effective mass means Me is small, which means it provides high electron mobilities. So what happens when effective mass Me decreases? When effective mass Me decreases, energy of electron levels in quantum well increases. That means smaller the Me, higher the temperature at which quantum transport can be observed. Clear? Now, the second condition is transport in mesoscopic physics should be ballistic. Means the dimensions of devices lesser than that of the mean free path or smaller than that of the mean free path of electrons.
എക്സ്ക്യൂസ് മീ മാം, സൗണ്ടിൽ
Yes.
ചെറിയ വേരിയേഷൻ വരുന്നുണ്ട്. മാമിന് ഒന്ന് സ്റ്റേബിൾ ആയിട്ട് ഒരു സ്ഥലത്ത് തന്നെ മൈക്ക് വെച്ചിട്ടൊന്ന് സംസാരിക്കാൻ പറ്റിയെങ്കിൽ നന്നായിരുന്നു.
Okay. Sure.
ഇത് ക്ലിയർ ആണ് മാം, ഈ പൊസിഷൻ ക്ലിയർ ആണ്.
Okay. So the transport in mesoscopic physics is ballistic. So what I was discussing is, so what is meant by mean free path? Mean free path or tau refers to the average length that an electron can travel freely before having a collision, and that collision could damage its momentum. So ballistic transport is observed when mean free path tau of electrons is longer than the dimensions of medium through which electron can travel. That means, basically it means dimensions of devices should be smaller than the mean free path. Then you can observe ballistic transport. So an analogy for this ballistic transport is a bullet shot from a gun. That means there is no scattering. Since ballistic transport has non-scattering property, electrons do not lose their phase coherence, and electrons can show phase interference effects in mesoscopic systems. So, what are the two main conditions required for a quantum transport? First condition is effective mass should be small. When the effective mass is small, we get high electron mobilities. And the second condition is transport should be ballistic. Means the dimensions of devices should be lesser than that of the mean free path. Now, next we are going to discuss quantum point contact or QPC. By definition, QPC is a narrow constriction between two wide electrically conducting regions with comparable to electronic wavelength. So what does that mean? So this QPCs were first by a Dutch team, Van Wees et al. parallelly by another British team, Varal et al. In 1988. So here you can see the structure for UPC. Here it is made with gallium arsenide, aluminum gallium arsenide heterojunction. The construction of aluminum gallium arsenide heterojunction is already being discussed in the first module. So what they did was a 2D electron gas was confined at the gallium arsenide, aluminum gallium arsenide interface in the interior of the heterojunction. Right. So this orange color shows the two-dimensional electron gas. Now, this 2D electron gas has a Fermi wavelength which is 100 times larger than that in a metal. So it is possible to study a constriction. Constriction means, so this is the constriction, right? So it is possible to study a constriction with an opening comparable to wavelength. So this constriction means this opening, this small opening is called a quantum point contact or QPC. Now, how do we make it? In a metal, point contact can be fabricated by pressing two wedges or needle-shaped pieces of materials together. But here, in order to make this QPC, the strategies are different. So what these people, Van Wees et al. Did in their study was point contact of adjustable width was created in the system using split gate techniques. So you can see two gates, split gate techniques. And this gate is negatively charged electrode on top of the heterojunction, which can deplete the electron gas beneath it. So you can see this is the this orange color is the electron gas, two-dimensional electron gas, which is in between the gallium arsenide, aluminum gallium arsenide heterojunction, and you have a split gate here, and you're applying a negative voltage on top of this gate. So as you can see from the construction, as you go from top to down, the height is different, the width is different, right? So by applying the voltage, by changing the voltage, you can vary the width. You can vary the width, and electrons are constrained to travel through a very small region or 1D region as a consequence of distribution in this electrical voltage which we apply on the gate. So basically, 2D became 1D. 2D direction became 1D. And the transport measurements of this 2D gas are made by employing contacts to this 2D electron gas on both sides. You can see contacts are there. It is with the help of these contacts, transport measurements are being done. Right. So this structure is called a quantum point contact. This now I have discussed the basic construction of what they did, what this scientist did in their work. So nowadays, different types of QPCs with different materials are being fabricated. So this is from their paper, Van Wees et al. 1988 paper, because it was the first quantum point contact which was invented. And now this quantum point contact can also be called as an electron waveguide, because the construction is similar to the normal waveguide which we use in electromagnetics, right? So that is regarding the construction of quantum point contact. And what did they find? These were the findings of their research work. So conductance is basically current per voltage, right? So what they observed was the width was varied by means of application of voltage on the gate, and conductance versus gate voltage was plotted. Now this graph shows only one value, like for the quantum conductance at 0.6 K as a function of gate voltage and quantum conductance, only one particular value, 0.6 K. But in their work, they have taken at different temperatures the variation between conductance and gate voltage. And what they observed was conductance and gate voltage do not vary linearly. But they observed that the values of conductance are quantized in particular multiples of 2e square by h. That means conductance varies in discrete levels or discrete steps of 2e square by h, and this value 2e square by h is the fundamental conductance, which we will discuss in the coming session. So the conductance is getting quantized as we increase the gate voltage. That is called quantization of conductance. This is what they have found from their research work. Means the values of conductance are quantized in multiples of particular particular fundamental conductance 2e square by h, and that is called the quantization of conductance. One more thing which was noted was, as a gate voltage defined in the constriction is made less negative, width of the point contact increases continuously. Right. So this was what they found using by creating the quantum point contact and what they analyzed from it. And that is where the quantum conductance, the concept of quantum conductance came into being. So we'll see that. So I already told that Van Wees et al. Was the first person who found this particular quantum point contact, and they discovered this concept of quantum conductance. Now, in order to understand the terms much better, we can try to derive the formula for this quantum conductance. Now, for this, consider a 1D mesoscopic semiconductor structure. Let it be a quantum wire. Okay. So this quantum wire is short enough that the transport is ballistic. I have already discussed what is a ballistic transport in the first slide, right? So the quantum wire should be short enough that the transport should be ballistic, and this quantum wire is connected through ideal leads. Ideal leads which do not provide any scattering. They are connected to two different reservoirs with Fermi levels EF1 and EF2. Right. This quantum wire is having ballistic transport. That means quantum wire do not provide any scattering. Similarly, the leads which are connected to the quantum wire, they also do not provide any scattering effects, and we are connecting them to reservoirs with Fermi levels EF1 and EF2. Hope the construction is clear. Now, observe a current flow. We should apply a small voltage V between the two reservoirs, so that potential between the two reservoirs will be EP, which is same as EF1 minus EF2. Right, difference between the Fermi levels is same as the potential energy. Now, in order to come to the conclusion, come to the formula for a current, the current across the wire will be given by the product of electron concentration multiplied by electron velocity multiplied by unit charge. When you consider the product of electron concentration multiplied by velocity, the electron concentration should be obtained from the density of states in the interval EV. Since we have considered a one-dimensional quantum wire, one-dimensional density of states in E multiplied by EV, because density of states in the energy interval EV will give the electron concentration multiplied by electron velocity multiplied by unit charge will provide the current. Right. Now, recall from first module, we have the formula for density of states of one-dimensional nanostructures as, I hope it's clear, N1D of E is equal to 2 by pi h bar nu. The nu stands for velocity, same term, velocity. Now, when you substitute this into this particular formula, what you get is a factor. Here you will, the term velocity will get cancelled, and you will get the term current is equal to 2e square v by h. The factor 2, this factor 2 is considered. Why? Because the electrons are moving only in a single direction. This factor 2 is not considered, but h bar is equal to h by 2 pi. That factor 2 is considered. So when you simplify this,
മാം ലാസ്റ്റ് സ്ലൈഡ് തൊട്ട് സൗണ്ടിന്റെ ഒരു ഇഷ്യൂ ഉണ്ട്. ഒരുപാട് സ്റ്റുഡൻസ് കേൾക്കുന്നില്ല എന്നുള്ള ഒരു ഫീഡ്ബാക്ക് ആണ് തരുന്നത്. നമുക്ക് സൗണ്ട് കുറച്ചുകൂടി ഇമ്പ്രൂവ് ചെയ്യാൻ പറ്റും മാം. പിന്നെ ലാസ്റ്റ് സ്ലൈഡ് തൊട്ട് ഒന്നുകൂടി നമുക്കൊന്ന് റിപ്പീറ്റ് ചെയ്താൽ നന്നായിരുന്നു എന്ന് തോന്നുന്നു.
സ്ലൈഡ് തൊട്ട് ഓക്കെ, ക്വാണ്ടം കണ്ടക്ടൻസ് തൊട്ട്.
അതെ അതെ, കുറച്ചുകൂടി ഓഡിയബിൾ ആവുന്ന രീതിയിൽ.
ഇപ്പൊ ഞാൻ പറയുമ്പോൾ ക്ലിയർ അല്ലേ?
ഇത് ക്ലിയർ ആണ് മാം. ഈ ഒരു വോയിസ് ആണ് വേണ്ടത്.
ഈ മൈക്രോഫോണിന്റെ ഇഷ്യൂ ആണോ എന്ന് അറിയില്ല.
ഓക്കെ, ഇത് ക്ലിയർ ആണ് മാം. ഇത് ക്ലിയർ ആണ് മാം.
ഓക്കെ, നോക്കട്ടെ. So I'll discuss once again. So in the last session we discussed how Van Wijs et al. Had produced the structure quantum point contact, and it is they who first found the concept of quantum conductance. Now, to understand quantum conductance better and to derive a formula for quantum conductance, consider a 1D mesoscopic semiconductor nanostructure. Let it be quantum wire. So this quantum wire is very short so that the transport is ballistic. These quantum wires are connected with the help of ideal leads to two different reservoirs which are characterized by Fermi levels EF1 and EF2. Now, quantum wire do not provide any scattering events. Similarly, the leads that are connected to the quantum wire, they also do not provide any scattering events. Now, in order to observe a current flow, we should apply a small voltage. We should apply a bias, right, between the two reservoirs. So now the potential energy between the two reservoirs will be equal to EB, which is same as the difference between the Fermi levels EF1 minus EF2. Now, to get a proper formula for conductance, we first find the current across the wire. Current across the wire is given by product of electron concentration, electron velocity, and unit charge. So when you take the electron concentration, that is obtained from density of states in the energy interval EV, right? So when you take the current, you will have density of states. In this case, we have considered a quantum wire. So density of states for one-dimensional nanostructure N1 of dE multiplied by EV, because it is obtained from density of states in the energy interval EV. That will give the electron concentration multiplied by velocity nu of E multiplied by unit charge. So that is how this formula came into being. I is equal to E N1 of D into E, V of E, nu of E multiplied by EV. Now, the density of states for one-dimensional nanostructure, the derivation for the formula, everything was covered in the first module. And recall, it's a formula like this. N1 of D is equal to 2 by pi h bar nu, where nu is the velocity. Now, when you substitute this N1 of D, means 2 by pi h bar nu into this equation, after simplifying, the velocity terms will get cancelled, and also this factor of 2 should not be considered. There is no need to consider. Why? Because electrons are moving in a single direction. And h bar is equal to h by 2 by. So that factor of 2 will be there. So when you simplify, the common terms are cancelled out, and when you simplify, you will get current is equal to 2 E square V by H. E square, V is the voltage, H is the Planck's constant. So that is how this formula came into being. Now, what is conductance? Conductance is current per voltage, current divided by voltage. So divide this equation by voltage. What will you get? 2E square by H. Now, this is the this value 2E square by H is the fundamental conductance, which we have found in the, which we have already seen in the last section, right? 2E square by H. Now, it is observed that this conductance of quantum wire will be independent of length. See, in the case of quantum transport, the conductance of quantum wire will be independent of length. But the classical case, conductance definitely varies with respect to, so that is the difference between the classical case and the quantum case. Now we are finding a value G naught, which is called quantum unit of conductance. And G naught will be equal to E square by H. And by taking the reciprocal of G naught, the reciprocal of conductance will be resistance, right? So we get quantum resistance value, reciprocal of this, R naught will be equal to H by E square. And by substituting values for H and E, we'll get a particular value, which is R naught equal to 25.812807 kilo ohms. So that is the, this is the derivation for fundamental conductance, and G naught, which is the quantum unit of conductance, and R naught, which is the quantum resistance value. Just have a look at this value, because we'll come to it in the coming session. R naught is equal to H by E square, which is 25.8 kilo ohm. So that is regarding the quantum conductance. Now, next is Landau formula. So till now, we have considered, what have we considered? We have considered one-dimensional nanostructure, right? One-dimensional nanostructure, which is having two leads, Now, when we are considering we have not considered the channels in the quantum wire. So we need some more generalized form for this conductance formula. So that generalization will result in a new formula, which is called the Landau formula. Now, to generalize the results, assume that or consider that the quantum wire is having many channels. The subbands, and channels, they're already, I hope you get the concept, because it is already being discussed in the first module. So the subbands are considered as channels in quantum transport. And suppose, so I told that there's in a quantum point contact, that constriction, which is called the quantum point contact, you're considering it similar to an electron waveguide. In an electron waveguide, you know that there are different channels, and you call TMN, where it is whether it is an electric field or magnetic field, you have different modes, right? Modes, TMN, like that. So similarly, suppose that the leads are injecting electrons into any channel. We are considering the quantum wire is having different channels. So, suppose that the leads are injecting electrons in any channel, or let it be called mode. Let it inject electrons into a particular mode M, and after interacting with a scattering center in the mesoscopic structure, electrons are emerging out through any other channel. Let it be N, or we can consider that let M be the mode through which electrons are entering, and N be the mode through which electrons are emerging out the channel. Then these electrons will make a contribution to the system, and total conductance be equal to the product of quantum conductance, which is 2E square by H, multiplied by quantum mechanical transmission probability, which is called mode TNM square, for electrons injected through channel M and they're emerging out through the channel N. So mode TNM, simply it expresses the transmission probability coefficients. And what are you doing here? You're taking the summation of all the coefficients starting from Nm to N, where N, capital N, is the number of quantum channels contributing to the conductance. Means if N is the total number of channels, quantum channels that are there in the quantum wire, M and N are the modes. The transmission probability will be summation of Nm to capital N, mode of Tnm, the whole square, multiplied by the fundamental quantum conductance value. That will give the final total conductance, and this formula is called the Landau formula. Okay, so Landau formula is a generalization where we are considering two leads and many channels. Is that clear? We are considering quantum wire with, here we have considered quantum wire with 2 leads, but we have not considered the channel. And then we have found what is the quantum conductance. Now we are finalizing it by considering the as many channels that are possible in that quantum wire, and we generalize it to a formula called Landau formula. Now, another thing which I have to say is there is one more formula called Landau-Buttigieg formula, which is used for multi-prop quantum transport, which is the quantum transport which is there with many leads and many subbands. Here we have considered only 2 leads and many subbands. But what if you connect many props or many leads, and if the channel is having different subbands as told now, we'll get a more generalized formula which is called the Landau-Buttigieg formula. So actually, I have not included it here. Just giving you the information because I think this, as per the syllabus, Landau formula is what you have to study for KTU. So Landau-Buttigieg formula is the modified Ohm's law in quantum transport. Right? You have to remember it. It is a modified Ohm's law in quantum transport. Now, another concept. So that is regarding the QPC and quantum conductance. I hope it's clear. The next concept which we are going to discuss is the Coulomb blockade. So till now, there are different types of MOSFETs which are being fabricated. And as we reduce the size, the magnitude of current also decreases, right? So the current flow in a MOSFET is due to number of electrons, many number of electrons. So can you imagine a device in which the current is transported by very single electron? Can you imagine it with a very single electron? Is it possible to fabricate a device? Yes. Such devices are now being invented. And such devices are called single electron transistors or SETs. So the basic working concept of SET is Coulomb blockade. So that is what we are going to discuss now, Coulomb blockade. Now, by definition, Coulomb blockade is the decrease in electrical conductance at small bias voltages of small electronic device comprising at least one low capacitance tunnel junction. For this, consider 0D nanostructure. Let it be a quantum dot. 0D nanostructure means it is confined in 3 directions and 0 dimension. Let it be a quantum dot. And if you consider a quantum dot, and even a change of one elementary charge to that system which is having quantum dot, it will make measurable effect on the electrical and transport properties of that quantum dot. Means the properties are going to get changed when you try to add elementary charges to the quantum dot. Now, that concept is the Coulomb blockade. I'm telling these are the definitions. I'll come to it. I'm coming to it. So, the Coulomb blockade is used in single electron transport devices, SETs, single electron memories. See, these are the devices which are now being invented and now they are under the field of research. So, for this, to understand this concept, consider semiconductor quantum dot connected to electron reservoirs at each side by potential barriers or tunnel junctions. So these are the tunnel junctions, and assume that the tunnel junctions are very thin. Tunnel junctions are thin enough to produce tunneling effect. So this is the sketch of that Coulomb blockade and that energy distribution. The second figure represents the energies of quantum dot when number of electrons in quantum dot, capital N, is changed in amounts of single unit charges. You're giving a voltage EV, and when you add single electron, what will be the energy change? That is what is being shown in this second diagram. It's a sketch of energy distribution in external voltages applied through the dot, the quantum dot. So you have a quantum dot, and then that is connected to reservoirs with the help of very thin tunnel junctions. Now, suppose that the number of electrons in the quantum dot is n. We are changing the number n of electrons in the dot by adding one electron at a time. We are adding only one electron at a time, and this electron needs to tunnel from, let it be, we are adding it to the left side, left reservoir to the dot. So if n is the capacity of the dot and we are adding one electron to that quantum dot, the potential energy required will be EV. Potential energy EV is to be supplied to the electron by means of an external voltage, right? As told before, we have to supply an external voltage and the potential energy will be equal to EV. Now, we know that in a capacitor, Q is equal to CV. So, the potential in a capacitor will be equal to CV square by 2. You can also write in another formula as this is same as Q square by 2C, the potential energy. So, that is the same energy which the quantum dot would be having. Means, suppose the quantum dot is having the charge Q. Here, suppose the quantum dot is having the charge Q and its capacitance is C, then the potential energy of the quantum dot will be Q square by 2C, right? Then we are providing a voltage, EV, right? So this EV will be equal to E square by 2C because the charge, the elementary charge which we are adding will be electronic charge, right? So Q will be equal to E, right? So E square by 2C, that is the energy that has to be provided to that electron for that electron to move into that electron to tunnel from one reservoir to the quantum dot, right? So this means, what does it mean? It means that for electron to enter the dot, the voltage should be raised to at least E by 2C. Okay, got it. Right. See, I'll let E be the potential energy we are providing to the electron to make for the electron to move from reservoir to the quantum dot, and the quantum dot is having a particular energy which is Q square by 2C. So that minimum energy we have to supply it with the help of the potential external bias, right? So that is same as E square by 2C. So we are discussing here in case of energy, EV is equal to E square by 2C. So what will be the voltage? V is equal to E by 2C, right? So the minimum voltage which we have to provide will be E by 2C. So what happens if the voltage is less than E by 2C? Electrons cannot tunnel. Electrons cannot tunnel from reservoir to the quantum dot. I hope you understood. Like quantum dot is having a particular charge which is Q square by 2C. That is the charge, that is a potential energy which we have to provide to the electron to make the electron move from reservoir to the quantum dot. So we have discussed now in terms of potential energy. So what will be the voltage? Voltage will be E by 2C. So we cannot give a voltage which is less than E by 2C. So we came to a conclusion that there is a voltage range between minus 2 by EC and E by 2C in which electrons cannot go through the dot, right? So even though you apply a voltage which is between minus 2 by EC minus E by 2C and plus E by 2C, the electrons, there you won't see any current. The current flow will not be there. So that is what is shown in the next graph. So just see the VI carrier of the quantum dot that is showing the Coulomb blockade. So what I said is there is a range minus E by C to plus E by C. Between this range, if you're providing voltage between this range, you will not see any current, right? But if you see a voltage, so minimum value of voltage to be given should be more than E by C. Now, what if we keep on adding more electrons? What if we keep on adding electrons? we can observe discontinuities in the current through the quantum dot when voltage acquires a value is given by V is equal to 1 by 2C, 2n plus 1 into E, where n can take values from 0, 1, 2, 3, etc. See, to understand this, let's take the second graph, figure 6, which is showing the charging of quantum dot capacitor as a function of voltage. It is normalized, okay? The charge is normalized and also voltage is also normalized. Suppose n equal to 0, V will be E by 2C, right? So when you normalize it, in the x-axis, it will be somewhere around 0.5 by 2C, 1 by 2C, E by 2C will be 0.5. So at 0.5, you're not seeing any, at 0.5 normalized voltage, you're not seeing any charge, right? So when the normalized voltage is 0, there is no charge. But when it is 0.5, you're seeing a charge 1. At the voltage, at the normalized voltage at value 0.5, you're seeing a charge 1. You can see that the charge and voltage are quantized. This is the Coulomb staircase. The Coulomb staircase means, according to this formula, according to this equation, it's like the quantization is happening according to this V is equal to 1 by 2C, 2n plus 2 E. Here you can see the Coulomb blockade. Okay, so next, so we have discussed what is Coulomb blockade, and we know that the minimum condition for electron to tunnel will be E should be equal to or greater than E by 2C. Understood? Now there are some conditions for which the Coulomb blockade effect to be clearly seen. So what are they? Conditions are there. The first one, when the size of the quantum dot is reduced, the capacitance value also gets reduced, and electric energy for electrons to enter the quantum dot increases. Simple words, the change in electrical energy should be greater than that of the thermal energy KT. It can be KT or KBT at working temperature. Or in other words, E square by C, that is the change in electrical energy, should be greater than KT. Or in another words, C, the capacitance should be much lesser than E square by KT. So that is the condition, which means the capacitance should be small, or we should work at a low temperature of 1 Kelvin. This is the first condition for Coulomb blockade effect to be seen. I hope you understood the concept, right? Like you're trying to keep an electron on the quantum dot. There is also electron. So there is a Coulomb repulsive force which is taking place. So that repulsive force is the Coulomb blockade effect. So once you overcome the Coulomb blockade effect, the current can start flowing. So in order to observe this condition, the first condition will be capacitance lesser than E square by K. And the next condition is number of electrons in the quantum dot should not fluctuate at equilibrium. So to understand this, let time taken to transfer an electron in and out of the quantum dot, let it be RTC, where RT is the equivalent resistance of tunnel barrier and C is the capacitance of the quantum dot. So fluctuations in the number of electrons in the quantum dot induce changes in potential energy of the order of E square by C. According to Heisenberg's uncertainty principle, delta E into delta T will be equal to E square by C, which is the change in potential energy, multiplied by RTC, where RT is the equivalent resistance of the barrier and C is the capacitance of the quantum dot. So this value delta E delta T should be greater than H. That means E square by C RTC should be greater than H. So when you simplify, C and C will get cancelled. And from this, you can get the formula RT should be much greater than H by E square. When you substitute the values, you'll get 25.8. This is the same value which we got, right? So as R naught. So equivalent resistance of the tunnel barrier. So the barrier which is there uh, between the reservoir and the quantum dot, the equivalent resistance of the tunnel barrier should be greater than 25 kilo ohm. Or in other words, you can say G should be the conductance. So these are the main conditions. First condition is you should work at a temperature which is greater than thermal energy kT. That implies C should be lesser than E square by kT. And the next condition is the tunnel barrier's resistance should be greater than 25 kilo ohm. Right. Now, next concept. So since we have understood what is Coulomb blockade, what are the conditions required to attain Coulomb blockade, we'll discuss like an application for Coulomb blockade, which is single electron transistor. Actually, this is a topic which comes in 6th module. But since we are discussing Coulomb blockade, I will discuss the basic concept of single electron transistor. So single electron transistor is a sensitive electronic device based on Coulomb blockade effect. So you know that we have a quantum dot. As before, we have a quantum dot. So we need three terminals, right? So what are they? It will be source, drain, and gate. Dot. We have a source, we have a drain, and we have a gate. So this quantum dot is like the reservoirs we had. Let the source and drain be the reservoirs, right? As before, when we were discussing the Coulomb blockade. So the quantum dot is connected to source and drain with the help of tunnel junctions, and the gate is coupled to quantum dot with the help of insulating material so that there is no tunneling which is here between the source and quantum dot and the drain. There is tunneling occurring between these sections, like quantum dot to drain, and from the quantum dot to the source there is there are tunnel junctions. But on this side, gate to quantum dot, there is no tunnel junction. It's insulated. So let the quantum dot has a total charge Ne, and this quantum dot is also called a Coulomb island. Okay, quantum dot is also called a Coulomb island. So this is how the construction of single electron transistor would be, and you will apply a voltage. So the very basic condition for a single electron transistor to occur is a Coulomb blockade. So in the Coulomb blockade effect, there are three conditions which are to be observed, which are to be finalized to see the Coulomb blockade effect in single electron transistors. So what is the first one? These three conditions we have already discussed and we have been discussing in the last section. So the first one is the bias voltage must be, I'm repeating it once again. Bias voltage should be lower than that of the elementary charge divided by self-capacitance of the island. That is, V bias should be less than E by 2C. Then the thermal energy must be below the charging energy, C less than E square by kT. And tunneling resistance should be, that is the resistance between the source to quantum dot and quantum dot to drain. The tunneling resistance should be greater than 25 kilo. So under these conditions, you can observe a blocking effect, because when you apply a voltage, when you apply, so this is another structure for this single electron transistor, which is having source, drain, tunnel junctions, and gate. So when you apply an external voltage, what happens is that it will induce a particular charge CVG, the opposite plate of this capacitor, and in order to compensate it, electron tunnels. Okay, I hope you know what is tunneling. Like tunneling is like electrons are moving from one device to another. So it is compensated by tunneling of a single electron. So it means electron tunnel from source to that particular quantum dot and then to the drain, right? So when you apply a voltage, it will induce a charge. Okay, it will induce a charge because there is no tunneling occurring here. Here, this is the path in which tunneling is occurring. Source to quantum dot and quantum dot to drain. But there is no tunneling occurring here. You're applying a voltage so that it will induce a charge, and to compensate the charge according to the and once the Coulomb blockade conditions are met. Okay, once the conditions which we have already discussed, once they are met, the electron tunnel from one source to quantum dot and quantum dot to drain, and then we say that there is a current flow, right? So what happens is that at that particular junction, at here, like here, you are inducing a charge with the help of voltage, and there is tunneling that is occurring place. Okay, so a competence between the induced charge and the electron that tunnels through the barrier is established. So that will result in a Coulomb oscillation. So this Coulomb oscillation will be recorded as the current variation IDS with respect to the gate voltage we are applying. So that is what is shown in this graph. IDS with respect to VG. You can see these are the Coulomb oscillations. I hope that concept is clear. Like this device basically works on Coulomb blockade effect. There is no tunneling occurring between the gate and the quantum dot. Tunneling occurs only between the source to quantum dot and quantum dot to drain. And you have to set the device as per the Coulomb blockade effect such a way that only one electron, because it is a single electron transistor, right? Only one electron should flow from source to quantum dot and quantum dot to drain, right? So you should follow the set conditions. You just follow the Coulomb blockade conditions, and this voltage will induce a charge, and due to it, there will be a competence which is occurring between the induced charge and the electron tunneling, and there will be oscillations, and that is called the Coulomb oscillations, which is recorded as the current IDS with respect to the gate voltage which we are providing, E by 2C, right? So now between two consecutive peaks, the number of electrons in the quantum dot is fixed and no current will be flowing. And if you measure the voltage between two consecutive peaks, you will observe the capacitance of the quantum dot. Measure the voltage difference between two consecutive peaks, you will get the capacitance of the quantum dot. Right. So this is the so I have discussed only the basic construction of a single electron transistor, how it is being constructed, and what are the conditions which are to be followed, and what happens, how the current is being formed in a single electron transistor. And single electron transistors have wide range of applications, like they're used as they can be substituted as inverters in CMOS. They have various other applications also as memory devices, etc., etc. So this is these are my references. So thank you. And if you have any doubts, you can ask.
Ma'am, can you show the reference page once more, ma'am, so that students can write it down?
Okay, sure. Okay, this is actually from their, the first reference is actually one of their textbook, which is already, I think most of them will be having the soft copy of the textbook. And the second one is from the paper. I have the copy, I can send it. And the next is an online course I attended, Nano Hub Nanoelectronics.
Ma'am, during the session, students have that concern that, ma'am, ഒരു PPT റൈറ്റ് സൈഡിൽ ഫോർമുലാസ് ചെറിയ അക്ഷരങ്ങളിൽ ഉണ്ടായിരുന്നു. അപ്പൊ സ്റ്റുഡൻസ് നോട്ട് ചെയ്യാൻ കുറച്ച് പ്രയാസമായിരുന്നു എന്ന് പറഞ്ഞ ഒരു ഭാഗമുണ്ട്. ഈ ഫോർമുലാസ് എഴുതിയിരുന്ന ചില സ്ഥലങ്ങൾ ഒന്നുകൂടി ഒന്ന് കാണിച്ചു കൊടുക്കാൻ പറ്റിയിരുന്ന ഒന്നായിരുന്നു.
Okay, sure. So here, okay, ഇവിടെയല്ലേ നമ്മൾ രണ്ട് ഫോർമുലാസ് എഴുതിയിട്ടുള്ളത്. Is it clear?
എനിക്ക് ലാപ്ടോപ്പിൽ
Is
ക്ലിയർ
it
ആണ്
clear?
മാം. മൊബൈൽ ഫോൺ വ്യൂ എങ്ങനെയായിരിക്കും എന്ന് എനിക്കറിയില്ല. മാമിന് അതൊന്ന് റീഡ് ചെയ്ത് കൊടുക്കാൻ പറ്റിയിരുന്നെങ്കിൽ നന്നാവായിരുന്നു.
Okay, okay. Actually, the formula is N1 of dE is equal to 2 by pi h bar nu. So I think you may be having this formula from first module. You may have derived it from the first module because this is one of the questions for university exam. N1 of d is equal to 2 by pi h bar nu. And I hope you got, you know how we got this formula. I is equal to density of states multiplied by unit charge multiplied by electron velocity. And you're substituting these this N1 of d directly into that current equation. But the factor of 2 is not considered because electron is moving only in a single direction. So the factor of 2 is not needed. But this factor, h bar is equal to h by 2 pi. So that 2 will come in the numerator. So when you simplify, I'll tell the E gets cancelled and the nu also gets cancelled. So E will be E square, 2 E square B by H. Okay, that is how it came. Pi also will get cancelled. I hope it is clear. Maybe you can do it yourself. Like this N1 of D, you know, it is 2 by pi h bar nu. Substitute it here. Substitute h bar equal to h by 2 pi. And one factor of 2 should not be considered. And h by 2 pi, it should come for h bar. Substitute, you'll get this final form. And another place where I showed the formula was here. Here, actually, the potential which we are giving is EV, right? So EV is given as E square by 2C. That EV, which is the potential energy, is equal to E square by 2C, which means E into E by 2C equal to EV. So when you cancel E from both sides, what will you get? The voltage. So this is the first one is the equation for potential energy. Now we are telling what will be the voltage. The voltage will be E by 2C, right? So that is how. And I hope this section is clear, right? Capacitor will have a particular charge, which is Q square by 2C. Sorry, quantum dot will have a charge, potential energy, which is Q square by 2C. And you are providing an electron to the quantum dot, should have a charge E square by 2C. So that is a potential energy. So what will be the voltage? The voltage will be E by 2C. So if you have that minimum voltage is V equal to or greater than E by 2C, then only the electrons can tunnel, right? Then only the electrons can tunnel from reservoir to the quantum dot. Suppose the voltage lesser than E by 2C, then tunneling will not occur in the reservoir. So that is one condition, the first condition for blockade effect to be seen. I hope concept is clear. Like actually, ഇപ്പോൾ പറയുകയാണെങ്കിൽ I'll tell already ഒരു കോഴ്സ് ഓൾറെഡി ആ ക്വാണ്ടം ഡോട്ടിന് ഒരു പൊട്ടൻഷ്യൽ എനർജി ഉണ്ട്. നമ്മൾ അതിലേക്ക് ഒരു ഇലക്ട്രോൺ ആഡ് ചെയ്യുമ്പോൾ ആ ഇലക്ട്രോൺ കാരണം ഓൾറെഡി ഇതിനുള്ള ചാർജ് ഇലക്ട്രോണിക് ചാർജ് ആണല്ലോ, ഇത് രണ്ടും തമ്മിൽ റിപ്പൾസീവ് ഫോഴ്സ് ഉണ്ടാവില്ല. ഈ റിപ്പൾസീവ് ഫോഴ്സ് ആണ് ശരിക്കും ഇലക്ട്രോൺ റിപ്പൾഷൻസ്, അതാണ് ശരിക്കും എന്ത് ബ്ലോക്കേഡ്. അതായത് ഒരു ബ്ലോക്കിംഗ് ഇഫക്റ്റ് വരെയാണ് കൂലും ബ്ലോക്കേഡ്. അപ്പൊ അത് കാണപ്പെടുന്നത് ഈ പർട്ടിക്കുലർ വോൾട്ടേജ്, when the voltage is equal to E by 2C or greater than E by 2C ആണെങ്കിൽ ഇലക്ട്രോൺസ് ടണൽ ചെയ്യുള്ളൂ. അപ്പൊ ഇതിന്റെ ഇടയിലാണ് ഈ ഒരു റേഞ്ച്, അതായത് E by നേരത്തെ കാണിച്ചു ബൈ സി, E by C, അതായത് ഈ രണ്ട് റേഞ്ചിന്റെ ഇടയിൽ എന്താ ശരിക്കും സംഭവിച്ചാൽ ടണൽ ചെയ്യാൻ പറ്റുന്നില്ല. അപ്പൊ അവിടെയാണ് ശരിക്കും എന്താ പറയാ, ഓൾറെഡി ഒരു ചാർജ് ഉള്ളത് കൊണ്ട്, ചാർജ് നിൽക്കുന്നത് കൊണ്ട് ഇലക്ട്രോൺ അത് ടണൽ ചെയ്യാൻ പറ്റാത്തത് കൊണ്ട് അവിടെ ഒരു കുലും ബ്ലോക്കേഡ് ഇഫക്റ്റ് കാണപ്പെടുന്നു. അപ്പൊ ആ ഒരു കണ്ടീഷനാണ് മോഡ് ബി, അതായത് ബയസ് വോൾട്ടേജ് ലെസ് ദാൻ E by 2C. ഇനി വോൾട്ടേജ് ഈക്വൽ ടു E by 2C ആവുമ്പോൾ മാത്രമേ ഇത് ബ്ലോക്കേഡ് ഇഫക്റ്റ് ഓവർകം ചെയ്ത് കറണ്ട്, അതായത് നമ്മൾ കൊടുക്കുന്ന ഇലക്ട്രോണ് ക്വാണ്ടം ഡോട്ടിലേക്ക് ടണൽ ചെയ്ത് പോകാൻ പറ്റുള്ളൂ. അതായത് ടണൽ ചെയ്താൽ മാത്രമല്ലേ ഒരു കറണ്ട് ഫ്ലോ ഉണ്ടാവുന്നുള്ളൂ. ഓക്കെ, സോ ദാറ്റ് ഇസ് ദ കൺസെപ്റ്റ്. അങ്ങനെയാണ് വരുന്നത്. കൂലംബ് ബ്ലോക്കേഡ് ഇഫക്റ്റ് എന്ന് പറയുന്നത് ഒരു റിപ്പൾസീവ് ഫോഴ്സ് ആണ്. അതിന്റെ കണ്ടീഷൻ ആണ് നമ്മൾ ഡിസ്കസ് ചെയ്തത്. ബേസ്ഡ് ഓൺ ദാറ്റ് സെയിം കണ്ടീഷൻ തന്നെയാണ് നമ്മൾ ഒരു കാര്യം കൂടെ പറഞ്ഞത്, ടണൽ റെസിസ്റ്റൻസ് ഷുഡ് ബി ഗ്രേറ്റർ ദാൻ 25 കിലോമിനേക്കാളും കൂടുതലായിരിക്കണം അവിടുത്തെ ടണൽ റെസിസ്റ്റൻസ്. പിന്നെ ഒരു കണ്ടീഷൻ, നമ്മൾ വർക്ക് ചെയ്യുന്ന, നമ്മൾ കൊടുക്കുന്ന വോൾട്ടേജ്, കൊടുക്കുന്ന എനർജി ഷുഡ് ബി ഗ്രേറ്റർ ദാൻ ദ എനർജി. ഇത്രയും കണ്ടീഷൻസ് ഫോളോ ചെയ്താൽ മാത്രമേ ഒരു ബ്ലോക്കേജ്, അതായത് അറ്റ് എ ടൈം ഒരു ഇലക്ട്രോണിൽ പോകാൻ പാടുള്ളൂ എന്ന രീതിയിലേക്ക് കൊണ്ടുവരാൻ വേണ്ടിയിട്ടാണ് കൂലംബ് ബ്ലോക്കേഡ് ഇഫക്റ്റ് ഉള്ളത്. ഐ ഹോപ്പ് ദിസ് ഇസ് ക്ലിയർ. പ്രജിത്ത്, ഹലോ
മാം, ഒരു എക്സാം പോയിന്റ് ഓഫ് വ്യൂല് ഈ ചാപ്റ്ററിൽ നിന്നും എക്സ്പെക്ടഡ് ക്വസ്റ്റ്യൻസ് ഫോർ എക്സാമിനേഷൻസ് കൂടി ഒന്ന് പറയാവോ?
ഓക്കെ ഓക്കെ, ഷുവർ പറയാം. ഇതില് മെയിൻ ആയിട്ട് ഫസ്റ്റ് വൺ സ്റ്റാർട്ട് ഫ്രം ദ ബിഗിനിങ്. ഇതില് വൺ ക്വസ്റ്റ്യൻ വിൽ ബി ഡിറൈവ് ദ ലാൻഡർ ഫോർമുല. അതൊരു 10 മാർക്സിനോളം വരെ ചോദിക്കാനുള്ള ചാൻസ് ഉണ്ട്. Then what are the conditions for Coulomb blockade? Another question will be what is a single electron transistor? Adinte conditions ചോദിക്കാം. Same തന്നെ, അതായത് when you have to write the condition, when you're telling about single electron transistor, ഈ മൂന്ന് conditions, first one, the bias voltage less than E by 2C, C much less than E square by KT, RT equal to, അതായത് RT much greater than H by E square, അതായത് ഓൾമോസ്റ്റ് 25 കിലോ എങ്കിലും വേണം. ഈ മൂന്ന് കണ്ടീഷൻസ് എഴുതിയിരിക്കണം. അതായത് കൂലംബ് ബ്ലോക്കേഡിന്റെ മെയിൻ മൂന്ന് കാര്യങ്ങളാണിത്. അത് സിംഗിൾ ഇലക്ട്രോൺ ട്രാൻസിസ്റ്റർ, അതായത് ഇതൊരു 6th മൊഡ്യൂളിലെ ടോപ്പിക് ആണ് സിംഗിൾ ഇലക്ട്രോൺ ട്രാൻസിസ്റ്റർ. അവിടെയും നമ്മൾ കൂലംബ് ബ്ലോക്കേഡിനെ കുറിച്ച് പഠിക്കുന്നുണ്ട്. ആസ് പെർ ദ സിലബസ് ഇറ്റ്സ് ഗിവൺ ലൈക്ക് ദാറ്റ്. സോ 5th മൊഡ്യൂളിലും കൂലംബ് ബ്ലോക്കേഡ് ഉണ്ട്. 6th മൊഡ്യൂളിൽ യുൽ ബി സ്റ്റഡിങ് ഡിഫറെന്റ് ഡിവൈസസ് ടുഗദർ വിത്ത് ഇറ്റ്. അതിൽ സിംഗിൾ ഇലക്ട്രോൺ ട്രാൻസിസ്റ്ററിനെ കുറിച്ചൊരു ക്വസ്റ്റ്യൻ വന്നാൽ കൂലംബ് ബ്ലോക്കേഡിനെ കുറിച്ചിട്ടുള്ള ഈ മൂന്ന് കാര്യങ്ങൾ, ഹൗ ടു ഒബ്സർവ് കൂലംബ് ബ്ലോക്കേഡ് ആണ് ഇതിലെ മെയിൻ പോയിന്റ്, കീ പോയിന്റ്, അത് എഴുതിയിരിക്കണം. പിന്നെ ചോദിക്കാവുന്ന ഒരു മെയിൻ സെക്ഷൻ ഈ ഒരു ഡെറിവേഷൻ, ലൈക്ക് ടു ഡിറൈവ് ലാൻഡർ ഫോർമുല എന്നൊരു ക്വസ്റ്റ്യൻ വരികയാണെങ്കിൽ യു ഷുഡ് സ്റ്റാർട്ട് ഫ്രം ഹിയർ. ലൈക്ക് എന്താണ് ക്വാണ്ടം കണ്ടക്ടൻസ്, എന്താണ് ക്വാണ്ടം പോയിന്റ് കോണ്ടാക്ട് എന്നൊരു സിമ്പിൾ വേർഡ്സിൽ എഴുതിയാൽ മതി. അതിനുശേഷം what is quantum conductance എന്നുള്ളത് with the help of this same diagram you have to derive it and show the current. നമ്മൾ ഈ പറഞ്ഞ കാര്യങ്ങളില്ലേ, അതായത് ഈ ഫോർമുല ഓൾറെഡി ഫസ്റ്റ് മൊഡ്യൂളിൽ ഡിറൈവ് ചെയ്തിട്ടുണ്ട്. അതും കൂടി കമ്പൈൻ ചെയ്ത് ഫൈനലി ഫണ്ടമെന്റൽ കണ്ടക്ടൻസ് G0 is equal to E by H square എന്ന് എഴുതിയിരിക്കണം. അതാണ് ഒരു കീ പോയിന്റ്. വേറൊരു കാര്യം, ഇതില് ലാൻഡോർ ഫോർമുല ഫൈനലി ഇതിലേക്ക്, അതായത് ട്രാൻസ്മിഷൻ പ്രോബബിലിറ്റിയും കൂടി സമേഷൻ എടുത്ത് മൾട്ടിപ്ലൈ ചെയ്ത് ക്വാണ്ടം കണ്ടക്ടൻസിന്റെ കൂടെ മൾട്ടിപ്ലൈ ചെയ്യുമ്പോഴാണ് ടോട്ടൽ ഓവറോൾ കണ്ടക്ടൻസ് കിട്ടുന്നത്. ഇത്രയും കാര്യങ്ങൾ എഴുതിയാൽ മാത്രമേ ലാൻഡോർ ഫോർമുലയുടെ ഡെറിവേഷൻ, അത് ഓൾമോസ്റ്റ് ഒരു 10 മാർക്സിനോളം വരെ ചോദിക്കാറുണ്ട്. സോ യു ഷുഡ് സ്റ്റാർട്ട് ഫ്രം ക്വാണ്ടം കണ്ടക്ടൻസ്, ഡയഗ്രാം വരയ്ക്കണം. അവിടെ തൊട്ടിട്ട് ഇപ്പോ പറഞ്ഞ ഈ ഒരു PPT നിന്ന് പുറകിലുള്ള ബാക്കി 2 PPTs പറഞ്ഞ ഇൻഫർമേഷൻ കൂടി ക്ലിയർ ആയിട്ട് പോയിന്റ് വൈസ് വിത്ത് ഡയഗ്രാം മെൻഷൻ ചെയ്തിരിക്കും.
മാം, നമ്മൾ ഓൾറെഡി 1 hour ക്രോസ് ചെയ്തിട്ടുണ്ട്. എന്നാൽ ഒരു ക്വസ്റ്റ്യൻ കൂടി എടുത്തിട്ട് നമുക്ക് വൈൻഡ് അപ്പ് ചെയ്യാൻ തോന്നുന്നു. സ്റ്റുഡൻസിന്റെ ഭാഗത്ത് നിന്ന് വന്ന ഒരു ക്വസ്റ്റ്യൻ, ഹൗ ദർ ഈസ് എ കോമ്പറ്റൻസ് ഹാപ്പനിങ് ഇൻ ബിറ്റ്വീൻ ദി ഇൻഡ്യൂസ്ഡ് ഇ ആൻഡ് ദി ഇ കമ്മിങ് ഫ്രം സോഴ്സ് ടു ഡ്രെയിൻ?
Here, ആക്ച്വലി നമ്മൾ എന്താ ചെയ്യുന്നത്, നമ്മൾ ഓൾറെഡി ഒരു വോൾട്ടേജ് അപ്ലൈ ചെയ്ത് ഒരു ഇൻഡ്യൂസ് കപ്പാസിറ്റൻസ് വഴി ഒരു പർട്ടിക്കുലർ ചാർജ് അവിടേക്ക് കൊടുക്കുകയാണ് അല്ലേ. സോ ഓൾറെഡി അവിടെ ഇലക്ട്രോൺ ടണൽ ചെയ്ത് വരുമ്പോൾ ഉള്ള ഒരു ചാർജും ഉണ്ടാവും അല്ലേ. അപ്പൊ ഇത് രണ്ടും തമ്മിൽ ഇലക്ട്രോൺസ് ആണല്ലോ, അപ്പൊ ഒരു റിപ്പൾസീവ് ഫോഴ്സ് ഉണ്ടാവും. അപ്പോൾ അത് കാരണമാണ് ഇവിടെ ഒരു എന്താ പറയാ ഒരു ഓസിലേഷൻസ് ഉണ്ടാവുന്നത്. അപ്പൊ ഒരു കറണ്ട് ഫ്ലോ എന്ന് പറയുന്നത് ആ ഓസിലേഷൻസ് കൊണ്ട് ഉണ്ടാവുന്ന ഒരു ഫാക്ടറാണ്. അപ്പൊ അങ്ങനെയാണ് ഡ്രെയിൻ ടു സോഴ്സ് ഒരു കറണ്ട് ഉണ്ടാവുന്നത്. അത് മെഷർ ചെയ്താലാണ് IDS എന്ന് പറഞ്ഞാൽ ഡ്രെയിൻ ടു സോഴ്സ് കറണ്ട് ഉണ്ടാവുന്നത്. അങ്ങനെയാണ് കുലുംബ് ഓസിലേഷൻസിന്റെ ആ ഒരു കോമ്പിറ്റൻസ് വരുന്നത്.
ഇല്ല മാം, നമുക്ക് ഓൾറെഡി നമ്മൾ 1 hour നമ്മുടെ ടൈം എക്സൈഡ് ചെയ്തിട്ടുണ്ട്. അതുകൊണ്ട് തന്നെ നമുക്ക് ഈ സെഷൻ വൈൻഡ് അപ്പ് ചെയ്യാം എന്ന് വിചാരിക്കുന്നു. ലാസ്റ്റ് 1 hour വളരെ ക്രിസ്റ്റൽ ക്ലിയർ ആയിട്ട് ഓരോ ടോപ്പിക്കും മാം PPT എക്സ്പ്ലെയിൻ ചെയ്തു തന്നു. നമ്മൾ ആവശ്യപ്പെട്ടപ്പോൾ റിപ്പീറ്റ് ചെയ്ത് തന്നിട്ടുണ്ട്. വളരെ വിശദമായി തന്നെ ഈ ഒരു വിഷയത്തിൽ ക്ലാസ് കൈകാര്യം ചെയ്ത മൃദുല മാമിന്, എൻറ്റയർ അസാപ് ടീമിന് വേണ്ടിയിട്ടും ഇന്നത്തെ ക്ലാസ് അറ്റൻഡ് ചെയ്ത മുഴുവൻ പാർട്ടിസിപ്പൻസിന്റെ പേരിലുള്ള നന്ദി ഞാൻ അറിയിക്കുകയാണ്. താങ്ക് യു വെരി മച്ച് മാം. ഇനിയും നമുക്ക് മറ്റു ക്ലാസ്സുകളിൽ കണ്ടുമുട്ടാൻ അവസരം ഉണ്ടാവട്ടെ എന്ന് ആഗ്രഹിക്കുന്നു.
Okay, thank you so much. Thank you so much, Vijit, and thank you, Priya and Prabha, for inviting me to this section. I also thank ASAP team for giving me a wonderful chance to take part in this webinar. Thank you so much.
Thank you, ma'am. Thank you so much.
ഇതിൽ സ്റ്റോപ്പ് ഷെയറിംഗ് ചെയ്യട്ടെ?
മാം ചെയ്തോളൂ. മാമിന് ലീവ് ചെയ്തോളൂ മാം.
ഓക്കെ, ബ്രിജിത്ത് എൻറ്റിവന്റ് കൊടുക്കാണ്.
ഓക്കെ.